Hello, my name is Lukas Bögel and I am the study assistant for the working group Digital Geography at the Department of Geography and Regional Research at the University of Vienna. In this video I will talk about regionalization and how it can be used as a pre-processing step in a predictive modeling workflow. And for this I will start with shortly explaining what regionalization is and how it leads to an additional independent variable that we can use in a predictive model. I will give an example with housing prices in California and compare the results of the RegRF, the Regionalized Random Forest method, to established methods like a casual random forest, but also other spatial approaches like geographically weighted regression and geographically weighted random forest. Before diving into the RegRF method, it is useful to quickly explain what regionalization is. It describes the procedure of grouping a large number of spatial objects into a smaller number of subsets of objects which are internally homogeneous and occupy continuous regions in space. It is often used by policymakers and spatial planners as it allows the grouping of administrative units of various scales into bigger regions. Applying policies to those regions instead of many smaller ones is an efficiency enhancement. In the example on the slide, 23 regions of similar housing prices have been created from the dataset on the left-hand side. As RegRF is based heavily on the casual random forest, it can be used for solving both regression and classification problems. The difference is that RegRF uses the region number each observation belongs to as an additional predictor variable. Experiments have shown that this can significantly boost the predictive performance of the models, both regarding the normal R-squared values, but also regarding spatial performance metrics like the number of insignificant LISA clusters. To implement RegRF, a few questions need to be answered. The most obvious one is how many regions to look for. There are few options for this. One of them is using unsupervised evaluation metrics like the Kalinski-Harabas index, but experiments have shown that the best predictive performance of RegRF is not connected with the best number of regions regarding this index. Of course, trial and error is also possible in cases where this is feasible for the user. Another question that needs to be addressed is which regionalization method to use. In the SPOP Python package, there are currently 5 regionalization methods available: WARD, AZP, K-means, Scatter, and MaxP. The choice on which one to use should be made depending on the situation and, more importantly, the dataset at hand. The size of the dataset is important as these methods have big differences in their computational complexity. Some of them only take a few seconds, others might take a few minutes or even hours, depending on the size of the dataset. Extensive experiments with those parameters and methods have shown that in fact these choices often do not matter too much. Of course, there are some combinations that work better than others, but a significant increase in predictive performance can be found no matter which method is used or how many regions are created. Let's look at this with an example from the real world. On the left of the small figure, we can see areas of housing prices in California. They have been grouped into 23 regions that have similar housing price characteristics, which are visible on the right side. Here, the regionalization method WARD was used. Now, housing prices have been predicted with 4 different methods: a normal random forest, geographically weighted regression, geographically weighted random forest, and, of course, the regionalized random forest. The experiment has shown the following. Casual random forest has an R-squared of 0.652 and 69% of LISA clusters are insignificant. GWR improves this by getting an R squared of 0.745 and 86% of insignificant LISA clusters. The geographically weighted random forest has the highest R squared at 0.766, with 84% of LISA clusters being insignificant for this. Regionalized random forest has an R squared of 0.741, with 78% of LISA clusters being insignificant, but it is also the fastest of the spatial methods. The differences in the runtime get more pronounced when increasing the sample size. Even for very large-scale datasets, regrf can compute in a reasonable amount of time, being about 10 times faster than GWR. The geographically weighted random forest was not able to finish computation at all for this experiment with the bigger dataset. Even after multiple days, it was still not finished. So to summarize, I would like to list the main advantages of the regrf method. Firstly, compared to the other two spatial approaches, it is very efficient regarding its computation. Also, it does not require the user to have prior knowledge about the study area, the parameters, or regionalization methods, as any of those combinations leads to a big increase in performance. As it uses the famous random forest algorithm, it is possible to use it for both regression and classification problems and makes it easy to implement. Thank you for watching the video on regionalized random forest. If you want to know more about it or the work we do in the digital geography group, please have a look at the description below.